week 2, which is we briefed you about the topic and what we're going to go through it. So yeah, we're getting into the design process for different type of structural members. And as we covered to you last week, the main steps or the key things you're going to be learning from the subject. Number 1, you're going to be able to estimate design actions based on local standards. When we say actions, it's going to be dead load, life load, which we're covering this week. Then the following 2 weeks, which are week 3 and 4, you will go through wind load. So you do have good 4 weeks of actions to learn from. And after this, that was the first component, is finding actions. The second component, designing steel members. Then the third one, designing timber members. So these are the main 3 components you are intended to learn. So this is we are here at the second week, dead and life load. You're gonna see most of what we're gonna be doing today is about reading details from the standards. Again, most of what we're gonna be doing is correctly reading details from standards and learning how this is happening. And I strongly suggest you to be on top of this topic before the start of next week, because we're going to have a lot of factors to deal with from the wind load standards, and things should smoothly go from there. Now, beside reading things from table, there is some, I can say, a mix between school. You know, you need to remember how we use density to find loads, and you did this at school level, and maybe mechanics of solid. So that's, again, you're going to need some sort of simple calculations. The other thing I will add, so reading from standards, simple calculations, and imagination. You're going to need to imagine how the loading will need to be calculated as, and this is going to come as we go through the examples, because it's a bit difficult to demonstrate now. Right, so again, the standards you will be using this week and continue from here on, it's the 1170.0 standard, which is to do or titled as general principles. In summary, this standard will give you the mix between different actions. That's one of the reasons we use it. There are others, but we will touch on them as we go. But for today, I will say the main purpose of the standards. I don't want to open the standard, so it does not cost me time, because I want to leave a good time for the examples to be demonstrated. So in this standard, the main thing, or what we're going to be mostly using this week, is how we mix dead load with life load, and other cases. Like in the coming weeks, we will end up mixing maybe dead load with wind load. But that's really the main reason why we're using this. The second standard you will be introduced to this week, it's titled as permanent imposed and other actions, but we're going to focus mostly or deal with permanent and imposed. So permanent, the trend usually we call it dead loads. Permanents are the dead loads, including the self-weight. The self-weight of a structure is dead load. There are also superimposed dead load, like tiles, like services. They are always there, and they are considered as permanent or dead load. Imposed, they are the life load. Furnitures are life load. The occupants are life load. So basically, these are the 2 documents, and that second document, it's 1170 part 1, right? Part 1. Got this table of contents, so we're going to have a few simple slides to go through about permanent loads. Yeah, section 1 is permanent loads, and they are really straightforward. If you have any questions, please feel free to unmute. Just stop me, just so we have more dynamic, engaging discussions, not about just listening and keep going. Things can be easily misunderstood, so keep asking to go to get things more clarified. So permanent actions, we're gonna have a lot of parameters. That's what designers, and I think you see these things with your hydraulic design or a design, there is also always factors. And one of the things you need to also get on top of is understanding the acronyms or factors we use. So G, right, in this whole subject will be considered as the dead load. I don't know why they chosen G to be dead load. It has nothing to do with P, permanent, or D, dead load, but just someone who likes it. So just, we can live with it. J is the dead load, and it's going to act continuously there. It's just there, sustained there, which is obviously the own weight does that. And also the covering and finishing sitting on our beams, slabs are always there as well. Without significant change in the magnitude, nothing going to change. So it's always going to be there, right? If we're designing a swimming pool, you cannot consider the water as dead load because they can remove it and putting it back. So it's only the loads which gonna stay. And as I mentioned before, the self-weight of dead loads comes mainly into two parts. One is the self-weight, and that's where you're gonna need to use some school skills to do this, which, as I said, the standard will not give you the formula to find the own weight. He will, you as the engineer should go and research for the densities for that construction material used to build a particular structure. Or if we're designing a concrete, we know that the concrete is 25, and that information is also available in the 1170.1 part 1. Which I said to you is to do with permanent. But they won't give you, the standard won't give you the pressure sitting on your beam or slab. They will give it the density, so you have to do that employ your school skills and the basic skills to convert that density, which is actually a 3D parameter. You know, density is a force divided by displacement to power 3. All right, it's like a Newton per meter cube or kilonewton per meter cube. So you need to convert that to a pressure in order to use for your calculation. And we're gonna see this and try to focus on those steps to get on top of what we're doing today. This statement here, or this line, is saying the self-weight. Yes, you can use tables A1. It's almost at the end of the standard. Table A1 and A2. They are about the end there, and then under appendix A1 and A2. Okay, and basically the standard lists the densities for the main materials used in construction. Okay, let me just activate this again just to help me. Right, so you see the unit here. It is kilonewton meter cube. So you cannot use this value and put it on the drawing or on your calculations. You have to change it to reflect what we are talking about. And this is what we're going to be talking about. And this is where students may have some mistakes during over the tests or exams. So again, there's two tables. One of them, the other one here, is talking about the materials used in the construction, like talking about ceilings, like plaster, and there are different names, different products. In our tests and exams, we're going to be very, very specific about which one to use. These are, again, these ones are given in pressure because the thickness is already defined by the product. All right, one thing you need to understand, make sure you paying attention to the unit. You will observe that table 2 is in function of a pressure already. It's kilonewton per meter square because the material is already defined by thickness. All right. So other materials like the ones here, they're giving you the raw density, which you need to convert to, depends on the thickness. And we're going to do these examples later on. This is just a quick reminder about what I mean with using the density parameter to determine the weight. If this was a cube with with constant lengths, 1 meter by 1 meter by 1 meter. So if I ask you to find the weight of this box, right? What you're going to do simply, I will just simply multiply the density, which if it was a concrete, pure concrete, not reinforced concrete, because reinforced concrete is 2,500, because it's got a little bit of steel inside it, but here it's pure concrete, it's 2,400, and this is again written in the tables I showed you here, right? It's just there. And so let's say if you've got that 1 meter cube of concrete, its weight gonna be multiplying the density by 1 by 1 by 1. So it's basically 2,400. And if you usually in the design we use this unit kilonewton as loading on the frame. So you just divide it over 100. And we talked about this last week. We said 1 kilonewton is about 100 kilograms. Same thing if that cube was steel, then we all know from that table we've seen, or from we search in the internet or find resources, 7,850 is the density of steel, and the point load and the load to carry this cube gonna be 75 eventually. So we just multiply 78.5 by 1 by 1 by 1 will give you 78.1 kilonewton. Now, while I'm here, let me do a quick exercise. You just need now, you remember I said to you, one of the things you need to employ to get over this topic is use imagination, okay? Let's assume this is just a piece of concrete. I know it's a cube and there is no slab that can come as a cube, because slabs usually are a much flatter object, something like this, yeah? But just this is a slab, a piece of rectangular concrete with a thickness. But I just want, given this is drafted for us, this example, let's say this is a slab. And if we need to determine the load that the crane driver, imagine this is a precast slab and they want to crane it and put it on site at its final position. So the driver will actually carry it from the 4 points like this, and he will have a cable connected to his crane, right, and carry it. Then if that driver will ask a question, okay, the driver will ask question and say, what is the maximum working load on my crane? So in this case, you need to find the point load. Okay, now all of you are going to say, yeah, that's making sense. It's clear. So what you're going to do here, you're going to say, let's say this was a concrete, as I said, it's concrete. So you're going to say the weight that we need to answer the driver with, it's going to be the 24 kilonewton per meter cube multiplied by 1 by 1 by 1, and that will give you 24 kilonewtons. Done? Easy. Now, let's imagine we ended up positioning this concrete cube or concrete slab in its final location. And its final location was about having another concrete beam or a steel beam sitting this side and another concrete beam sitting the other side. Okay? That was the final location where the crane placed the slab. Now, I want to ask you, what type of loading each beam gonna carry? Is it a point load or something else? Can someone answer?
A line load.
Excellent. That was the answer. I just want, so this, how we will not give you this answer in that example. You need to imagine it, because basically the load here gonna be distributed like this. This is a line load. This red beam will end up carrying a line load, whether you like it or not, because that's how the slab is sitting on the beam. It's not sitting by a point load. And this is kind of the thing, this is the level of thinking we need to go through to determine loadings. Loadings is not only about picking numbers from tables or making those simple calculations, also imagining what's really happening. And I just want to bring this so things will go easier to you as we progress further with the topic. Now, how to calculate this? It also need to switch on some imagination there. Simply, there are different ways. And it depends on how you are experienced and developed expertise on doing it. And that means depends on have you done your homework on time and repeated it, and don't just look at the calculations we give you by videos or by the PDFs and think that if I'm gonna do it 2 days from the test, I will go on it. We're gonna tweak the questions and change it here and there, and you're gonna have things upside down. And after you spend careful time on it, you're going to see that was. So, right. So how to find the loads on each one? One of the methods, it's okay, go and find the imagined point load, right, which was 24 kilonewton, which I did with you before the crane was carrying it with. Then distribute it over the beam. So before I go and give you the answer, because you're going to have many examples to do, can someone tell me how I can work out the line load, this one, from the 24?
So you'd convert the point load into a line load by distributing it over 1 meter.
Excellent. So you said to me, I will divide 24 over this length. And you know, the process of dividing, it means you are distributing the load. Excellent. So is that enough, or there is something else to do?
You need to split it because there's 2 line loads.
Excellent. You need then to divide it over 2, or in other words, multiply it by half. Yeah, which is because here it's a meter. So that's really gonna distribute, if you're gonna divide it. So students just said, first of all, we're gonna divide it over the this length. That will distribute it to a large magnitude. Then remember, we have 2 ends carrying this block. Then you have to either divide it by this length or half it. So my point from this demonstration is just remember there is some sort of imagination you just need to employ to go over the examples coming to you and the ones we're going to do tomorrow as well. Okay, so let me stop here and just continue some simple facts, which we already talked about. So based on the figures, okay, that we have here, you can always consider that the weight of concrete obviously is 2.5 or 2.4 more than water, because obviously that's true, because the density of the water is just 1,000 kilograms per meter cube, as you all know. And with the steel, the steel is 8 times heavier than the this concrete. Sorry, the water tank, the water. So if it was water, okay, making sense. That's just for you to. Right. So now we're gonna jump to section 2. So you can see that's all. Yeah, but you see, as I said to you, dead load, it's just picking things from the standard or reading the question carefully, because sometimes in our example, we have special materials. Like even nowadays, there's a lot of new architectural materials, whether wall covering or floor covering, and they are not on the standard. So we just need to search for them or ask the supplier for such information. So yes, the thing is all about correctly reading the question and the standard and going through this calculation process we start discussing. Number 2, imposed actions, life loads. They are much more easier. The good thing with life loads, and you're gonna experience this when we solve the problems, you're gonna see when we do dead loads, it may take half a page, but life load, it's only two, 3 lines. It's not a lot. Why? because usually the tables in our standards, they give you the life loads in kPa. What does kPa means? It's already a pressure, right? The loads will come to us as a pressure, and what we need to do from there, just multiply it by what we call it floor load width. So if I jump quickly to this cube example we discussed, after we placed the slab and I said to you quickly, there is a beam here and another beam here. Forget about dead load, life load. You're going to go open the standard and think, is that a house? Is it a hospital? Is it an office building? And the standards will tell you use this much of kPa. Let's say for a house, they're going to say use 1.5 kPa. That means 100 kilograms per meter square, which is just a pressure, like a pressure. No unline load, not a point load. kPa. kPa is a pressure. Okay, then how to find the line load caused or imposed on this side? Can someone just quickly tell me? I'm going to multiply 1.5 by what?
By 1.
Just give it another think. Thanks for trying. Again, you're going to multiply 1.5 by what?
Oh, the surface area, was it? 1 times 1.
All right, this pressure, it's actually still applied. I'll just move it down. It's still applied down the page. Just delete those additional circles. So imagine this is the pressure, yeah? It's like a blanket. You imagine you have laid a blanket on the floor, but it's heavier. It's 1.1. So it's a pressure. And what I'm asking you, can you tell me what, any one of you, can you tell me what line load we eventually having from this pressure? Remember, line load units are kilonewton per meters. So how to calculate this? The answer is multiply the pressure by what we call it the floor load width. The floor load width is half of this span. So this span was 1 meters. Half of it is 0.5. So the answer is multiplying 1.5 by 0.5. Then the load is 0.75 kilonewton per meter. Okay. We call 0.5 as floor load width or roof load width, whatever we're designing. If we're designing a floor, we call it floor load width. It means that how many, what distance does the support and subject carries? Now this side is carrying half of the floor and the other side is carrying the other half. So you're only going to take 0.5 coming onto this right-hand side, right? So mathematically, what does that mean? You have to multiply 1.5 by 0.5. Remember, we did this in the dead load as well, but the dead load got a different story because we're starting from density, from meter cube. Okay? We will do this slowly on many coming examples. I just want to finish the notes on time. So anyone want to discuss or ask or any questions about what I did? Is it kind of making sense why we're multiplying 0.5 by 1.5 to get to the line load? Any questions about this? Right. So we were talking about life load, and I said to you the standards, the good thing with the standards, they typically gonna give us the life load in kPa, and as we said, depends on the type of the building, whether it's dwelling like residential, but there are other cases than self-contained dwellings. There are offices, and there are other pages on your standards which talks about hospital and what else, gym and sport activities, whatever. So there are much more cases to consider, and obviously whenever we have more crowded people, the load's going to be much higher. Whenever we have floors with fixed with fixed chairs, like in movie theaters or so, the loads will be higher because they know people cannot move as easily as required there, and things will be more critical. Now, someone may ask me the question, why do we have two type of loadings here? Why we got the blanket or the pressure and also the kilonewton? When the designer gonna make a design for like a simply supported, like let's say this is a simply supported slab or beam, whatever you like, we have to design it for both of these two cases separately. So we have to design it as if it is under a pressure load, right? Like if we're talking about a residential, so it's 1.5 pressure load. And in a new design, like take away the pressure, you have to design it as well for a line or point load, depends on the standard. So usually for life load, we have to consider the two case studies. Why this is happening? Because maybe the occupants will gather at specific point within the floor, right? So that's why we have to look at two different situations where the load is actually distributed, and when the load is gathered and at one point, that gathered or concentrated load will be given differently by the standard. It's something the standards will tell us what to use. Now, someone can say, does that mean in the exam or test we're gonna tell you what to do? We're gonna tell you design it for this case or that case or none or whatever. So we won't tell you take this floor and go design it. We're gonna tell you which loading cases you should cover. But ideally, just like in real design, engineers need to check both situations separately. That's the point. All right, so I trust we covered all the points or statements mentioned on this slide. Yeah, now given that it's dependent on the time, then that's where we have different figures. Yes, they are assumed to be uniformly distributed. It's a blanket, it's just a KPA. However, as I said to you, the standard will ask us to always check for a case where we have a point load in the middle to check what's going to happen there. All right, next here we do have some simple examples or just some reminders about the units. So we talked about this maybe last week during the workshop. So there is a characteristic life load that these are the loads that we pick and take from the tables. And as again restated here, is taken from that part 1 standard. So typically for houses 1.5, 3 for office, lecture theaters 3 as well. And this is the sport centers, it's 5 kPa. And again, as I said, it is, I think, yeah, this 3 should be 5 actually. Yeah, this little 3 should be 5. Okay, so it should be 500 kilograms per meter cube. Any questions you got there? Yeah, as I've already discussed, this depends on the usage, and it's up to Mr. Standards to tell us what load we should consider for a particular building. So just letting you imagine also these 3 kPa, it represents 3 kilonewtons per meter square. So it's about 3 of 100 kilogram people standing in 1 kPa, right? In 1 meter square. So 3 people standing next to each other, and this is just comes from standards and well adopted in the design industry. Maybe we have a quick example here to go through. The standards will give you life loads in kPa, which is I see it as a simplification, unlike dead load, where you're still gonna need to work out things maybe from the density property from that, and you work it out. How do we apply life loads? It's again that imagination thing. You need to imagine what's happening there. We need to change life loads into kilonewtons. That's exactly what I was talking to you, and try to practice this with the examples. Make sure you're on top of this when you practice, and try to imagine things in different ways and different directions. And here we have an example. So we have a bridge. This is a walkway bridge, and simply they're trying to determine the load over the bridge, okay, in terms of kilonewton per meter. And I think we do have some sort of more images here about it. So basically, the bridge platform, regardless whether dead or live load, it will end up causing a pressure as shown here. So we're talking here about imposed live load, so don't worry about the dead load at this stage. When we're talking about live load, it was a bridge, and we wanted to determine the line load as per this question. So don't get confused, because in this example, they want you to determine the line load over the bridge. You remember in mechanics of solids, we used to give you the examples like this. That's how we used to give you the examples to work on, and sometimes we tell you maybe there's a point load here or a higher load there, it doesn't matter. So the question is how we estimate this line load for the live load case. Don't worry about dead load. First thing, we need to know what type of loadings the standards will ask us to impose here. We just need to read the standards. Let's say it's 5 kPa. Then basically, to determine the line load, we will then multiply it by the width. So if I need to determine the load, let me just change my pen. Yeah, it is okay. If I want to determine the load, which is simulating the overall line load across the bridge, then I want to determine, sorry, let me just make it look a little bit nicer. So this is the load we're trying to estimate over the bridge. And if I need to determine as a kilonewton per meter, I would go to the standards. The standards will give it to you in kilonewton per meter square, right? And what does kilonewton per meter square mean? It is actually a pressure like this distributed all over the floor of the bridge. And then if I need to convert it to a line load, that represents the whole story, and then I can take it and do whatever I have to do in terms of what you studied in Structures 1 or Mechanics of Solids. You have to convert it to this line load. How to do this? Simply, we're going to multiply the pressure by this width. This width here, that's what we're saying at the end. Multiply the pressure by the width. Now, that will give us this profile. What about if I want to find imagine here I got a concrete wall. You with me? I've got, say, a concrete, let me clean it up a little bit. Let me clean it up. And imagine I have a concrete wall. This is a concrete wall which carries the bridge. And I want then to determine this loading here. Can someone tell me how I can find, let me call it H. How can I find this line load H?
You would multiply the pressure by the length of the bridge.
What is the length of the bridge? If I say this was 20 meters, what's the length of the bridge?
20.
Okay, well, thanks for trying. But when you say 20, that means you are ignoring this side. When you say 20, you are saying the whole span is actually carried by this poor guy. But isn't it someone else here is carrying it? So do you want to change your mind here, or?
So would it be half the length?
Correct. It will be half. It will be 10. And that 10 is the floor load width I'm talking about. So I remember I was saying this just to make me, the standards, they just give us the recipes, they gave us the parameters, they will not give you the steps. The standard will not tell you what to do. That's what you need to learn and use your engineering skills to do. So determining floor load width or roof load width and understanding which direction I should worry about is part of the skill you're supposed to develop with this topic. Okay. So as I said to you, in this walked example, their interest was about finding the line load that they will end up using to find how we are stressing the floor of the bridge. Remember the bending moment diagram, shear force diagram? These guys gonna come from finding this line, this purple line load. Okay, to find this purple line load, we have to multiply the pressure by B, which will change the pressure into line load. However, if in a test or exam, we're asking you to find the line load on this support, and obviously there's another support, you need to know this. Because we told you from this picture, well, obviously the bridge needs to be carried here and there. You cannot have one side, it's going to fall down, isn't it? You have something here and something here. So that means I will then multiply Q, the pressure, in order to determine which color you like here. I put orange. Okay, orange. So I want to determine the orange line load. You need to build that understanding and say, I'm going to multiply the pressure by half of the bridge's span. And that will give me the orange line load. So you need to know the floor load width. Okay. Do we have any questions here? Okay, so there's some numbers on what we just said. Again, the question here was asking us to find the line load that we were talking about here. They were after the line load. They're not interested in my story about the wall. I just want you to look at it differently. So they want the line load. What they did, they multiplied the width of the bridge, which was, it looks too small for me than the picture. So it's about half a meter, which does not make sense. But anyway, just live with it. So we're going to multiply the pressure, which is the load on a bridge from Mr. Standards, multiply it by the width, which is 3 kilonewton per meter. So your simple loading line diagram will look like this, 3 kilonewton per meter. See here, my problem, or as a designer, I want to design the bridge floor. So this is my slab that I'm going to go and find the action zone, dead load, bending moment diagram, shear force diagram, and then I'm going to do what we're going to teach you to do from week 5 and so on, right? Which is to do with the steel design, or next year you will study concrete, etc. However, this whole story will change if I'm going to tell you, no, I want to design this support, this guy here. Then you have to multiply what? Can someone tell me the numbers? You're going to Q. You're going to be what here? If I want to find the line load on the support, just the numbers. Which so two numbers? Yeah.
5 times 5, which is 25.
Correct. It's going to be half of this, which is 5 meters, multiplied by 5, which is the pressure, and this will give us 25 kilonewton per meters. Then I'm going to go to put the load on my wall and design the wall. Right. So that's really all about, these are the main things you're going to be doing and calculating, etc. There are 2 other sections I need to scan through within the 16 minutes I have. And section 3 talking about how we combine actions. I will give you a quick background about it. Then I will show you how it's really simple. It's in terms of calculations and what we really do, it's a 1 or 2 lines a step. Don't think it's very long. It's 1 or 2 lines a step. It's all about how we mix the loads together. Okay, there are factors, and there's a bit of story about those factors, which I will take you through. But the main thing you need to know is from where to read these combinations, and that's all, how to apply them. In terms of doing the calculations on your calculation sheets, it's only one line a step or 2 lines. It's not a big deal. The other section going to be talking to you about the limit state method, which is again just preparing you to what's going to happen in the design, which is starting in week 4 after the wind loads. It's a limit state design. Simply, we're going to compare actions with the strength by considering the standards recipes, which is the combinations, etc. So talking about combinations, just a quick story before I show you what are those combinations. Combinations are the safety factors, which we have to apply to dead load or live load. All right. Now, here we have a quick story telling us why people decided on those factors. The thing is, ages ago when they started building standards in different countries, they made a survey about how frequently a floor for an office, for example, is loaded. And they find typically, like this vertical axis is the probability of occurrence. So the reoccurrence for that loading, they found mostly 0.8 kPa, which is 80 kilograms per meter square. It's not a lot, actually. 0.8 kPa is frequently the load applied on X type of floor, right? However, there was a very few situations where the loading goes up to 2.5 kPa. Now, the question is here, are we deciding between these two, here or there? Next slide will tell you, no, there is some statistics people have gone through, and that's how the standards are developed. Those statistics will help us to determine what we call a characteristic load. There is a characteristic load, which is the load we actually take from the standard. So those loads on the standards, they're calling them characteristic loads, and they taken based on these calculations. So the 1.5 from the table, or 3 for an office, or 4 for a university, or 3, whatever it was. It's called a characteristic load, and it came from applying this curve, the bell curve, and it's actually chosen at a point where we have 5% chance for this load to exceed, right? This is how the process is. So they're going to apply statistics, then they're going to see how I can find this figure here. So this figure represents the 5% chance, okay, represents 5% chance for that maximum load to not be compromised, in other words. Now, if you think about it a little bit deeply, again, you're going to say, but there is a still chance that people going to misuse that floor. Like, for example, if we have a floor in our house, it was just a bedroom, then we suddenly change it to a storage, and you keep filling it with some old things or furniture you're not using. So here, actually, you change the loads. You're changing the loads from 1.5 to higher. So this is what we're talking about. So there is still chance. And the question here, this chance is a bit risky, because 5% means there is 1 in 20 chances for that load to exceed. So that's even the 5% I was talking to you about here. It's still risky, because we can't exceed it. So how to solve this problem is we use the safety factors, full stop. So because whatever figure you're gonna say, there's always chance people gonna misuse it, and then you will okay, and then from here the standard said we have to use safety factors, and that's where it's gonna take us to the combinations, etc. So those safety factors, which are summarized to you here, they are just numbers. They are taken from AS 1170 part 0. You know, the first standard I said to use. So for dead load and live loads, we're going to use part 1. Those tables I showed you for dead and live loads, they were used for from part 1. But those recipes and those combinations, they're coming from this part, and that's what you're going to see slowly through the examples. right? So this is really the summary. Is the standard will tell you if you're mixing dead with live, you have to use 1.2 for dead as a safety factor and 1.5 for live as a safety factor. If you only have a structures with dead load only, maybe you're going to have a structure with dead load, then the factor of safety going to be 1.35. This is just, I memorized it from, and if there is earthquake with wind, then things will keep changing from here and the recipes will. So this is really what we mean with combinations of actions. And yeah, so that's really the story. So it's really easy. It's just you need to correctly again read the drawing. It's easier than finding dead loads and live loads. Really, nothing than that. When if we're talking about how to find the ultimate loads, because one thing I want you to understand, if you're going to apply this recipe, we're going to find what we call it ultimate load, the ultimate action. And this word, the ED or the ultimate load, it's part of the limit state design method that I will brief you about at the end of this hour. Okay, this is kind of the argumental equation we're using to design. I will come to this later, but in summary, this recipe or this combination will give us the ultimate, the highest possible loads that structure gonna experience or supposed to be carrying. All right, so that means you are following the standards, the limit state design method. Here we have really very simple example, and I don't see anything complicated with it. They just want you to, because yeah, sense how it works. So for example, if we need to find the line load running over this kind of frame, what are we doing here? We're assuming the length of, we have 1 meter length of this slab. We're going to do much more comprehensive examples. So this is 1 meter width for the floor. And we need to find the line load, this orange line load. How to find it? We're just going to go through what I showed you just before. We have a density for the concrete, because here we want to find dead load G and live load Q. I think I've already told you dead load is G and usually live load is Q, right? So to find the line load that will represent, again, if I take you back to mechanics of solids, we used to show you things much more friendly and simplified, like those supports and tick, 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 that's it. So we give you this ready and just go and find us the actions. But here, you need to go from the start and actually find the actions to us. So how to find this line load? You simply just going to multiply the pressures by 1 meter width. Now, as I said, for the dead load, we have to go to the density. To convert the density, we're going to multiply it. We're going to multiply the density by B by T. Okay. Oops. One of the, you can see here, so 25 kilonewton per meter cube by 0.12. What's 0.12? Is the thickness of the concrete by 1. What's 1? It is the width. I strongly suggest you this week when you practice the examples, try to put the units here. Try just only for this time. Try to put the units here, kilonewton per meter cube. This was just meters. We converted it. Don't get confused. This was up here millimeters, but it's converted to meters. And this is 1 meter already. It is the width we are studying. So we're trying to represent what 1 meter width will cause on as a line load on this system. So that's how we ended up finding 3 kilonewton per meters. Okay, that's one answer. This is the dead load. What about live load? As I said to you before, it's just a one line, right? You don't need to do through many steps. You're just going to multiply the pressure by the 1 meter. That's it. Because the standard always going to give you the pressure. And for this case, if you read the question, it was, I think, what did they say here? They gave you the live load straight away. You even don't need to look at the standards. They said it's 4 kPa. So you're simply going to multiply 4 kPa by 1, which is the width. There's one thing I want to mention to you is with dead load, the first dead load here we calculated was the own weight. But the question said there is a superimposed dead load. Superimposed dead load, it is the covering. It is the services like the plaster that you have If you look all upwards, I think you're all sitting in a room. If you look up, you're going to see a plaster. That white plaster got its own weight. You have to add it to the dead load. All right. So that's what they did here. If people don't know and you're going to see a lot of examples like this in our examples and even workshop questions tomorrow. So that's here. Now, after you're gonna define your Q and G, G was 3. Sorry, no, I'm 3 is not full. The total dead load was 4, and the total life load was 4 as well. So this is our full G and full Q. Then here you can come to those recipes. And as I said to you before, in this subject, you're mostly going to be actually going to have wind load as well, and you're going to deal with these mixes. Yeah, you're going to deal with some mixes because we're going to teach you in some of our examples, stability limit state, services limit state. So as I said, these are the combinations. It's just the way we combine loads, which depends on two main things. Again, 2 main things. What are the 2 main things? The first one is what type of loads are in the game, in the party. So, in some cases, we're going to have dead load, dead life load. So mix them like this. In some cases, we have only dead load. So just multiply it by this. In some other standards, as we say, we talk about earthquake, we have different mix, which we will not do in this subject. That was one thing. The other thing depends on what limit state we are worrying about. This may be not very clear because you're going to understand this hopefully when we go through one of the examples tomorrow, or also when we start talking about deflections. If you're designing things for strength, right? What does strength mean? Strength means you are checking the beam not to break, right? Because when you design a concrete or steel or timber beam, you have to, one of the first checks, you make sure it will not break. So you are checking stresses and strength. So you have to use these recipes. Okay, if you're designing the stability of the beam, stability of the beam means that the beam will not the structure will not overturn. So, for example, a retaining wall like this, you've got a high ground and a low ground. You may see this in a garden or in the street or somewhere. You are standing here, yeah. So stability means one of the checks that structural engineers do is they make sure that it's not only about the strength, that we need to make sure this L shape will not break. It also, we need to make sure the whole thing will not turn, as a one piece and fall. We call this a stability check. We're going to do this check in one of our worked examples in the workshop as well. So if you are making this check, you have to use these recipes. They may be same or not, but this is how the standard states it. Serviceability, it's deflection, sagging. Like if I come back to this retaining wall, we need to check, you need to check how much this wall gonna actually deflect like this, because it's gonna deflect. Anything deflects. If you walk on your floor, it's actually deflecting by 1 or 2 millimeters. You don't feel it because the engineer who did it was really good. He didn't. He designed something proper, and you can't feel the deflection. So everything deflects. So when you're gonna do this check, you have to use these recipes. Okay. So I'm done with the recipes. There are few. Okay, that was the stability check. I think I was trying to remember. This, you can see, this picture just tell you it failed due to, I would say, stability, because the beam did not break, the floor did not break, but the whole thing fall down. I would say it's a stability thing. So I think my time is almost done, but I'll try to really cover this easily, and I'm sure people will touch on things. Limit state design method. It is simply just using the argumental equation, which will tell us whether the structure is fit or unfit. That's all. So what does it really mean in terms of equations? We're going to compare the design actions, right? We're going to compare the design actions, and we're going to make sure the capacity I really forgot how there are a couple of, here we go. This is going to help me. I'm trying to talk about this. So what we do here, we go and calculate the actions, which we're teaching you this week and the wind load in the coming 2 weeks. ED means they are the actions, whether wind, whether dead load and life loads, whatever the case is. And then we're going to compare it. We're going to make sure they are less than the capacity. So obviously we have to make sure the actions will cause stresses equal or less than the capacity. Now this, we're going to do this from week 4. The RD, because you will not see it in our work from now until we finish wind load, because from now until wind load, we're playing with actions, whether from dead load, life load, wind load. We're finding this guy, ED, the design actions. RD, it's a design. It's about how strong is the member to resist actions. And we will start touching on this when we start talking about steel design, which I believe is going to be week 5 or 4, right? And you can see, remember here we talked about safety factor, which is 1.2 for dead, 1.5 for life. Again, there is safety here. When we find capacities, we're going to have also, so I just want you to sense how safe are the standards, okay? Just to make sure things will be, and those factors of safeties for the design, we will revisit these things, okay? So I suggest you, I think I'm done really, but there are, I suggest you all, we always to go through these notes. If you have any questions, we can discuss them over the workshops, but we will revisit these things when we get to them. Yeah, thanks, Vipul. I think you would have more interesting things with the examples. Thank you.
I've just witnessed will be demonstrated in the great details with this example. There are 5 examples that we're going to cover. Not super complicated. They are simple, but as Heather mentions, they require a bit of imaginations. Your right, left, and left brains need to work together. So one will do the calculation, another will do the imaginations. But these examples will help you to activate your imaginations as we go forward. Of course, unmute, put the question in the chat if you have any questions, if you don't understand, if I go too fast. I hope you have a standards handy, 1170.0 and 1170.1. That will be the useful to. We need to calculate the self weight of 600 by 300 millimeters of reinforced concrete beam. So if I have these 300 by 600 millimeters cross sections of the beam, we need to calculate uniformly distributed load and total load. So what we have, this is support. So I think, let's say this is supports and this is another supports. This is the beam and this is 5000 millimeters given here. What they want to calculate the weight. The beam will carry their own weight. What would be the load that is coming on here, and what would be the point load for the same beam that is coming onto here? Let's say give them N, and what would be the point load? So that's the questions. now basically the equations are there is only one equation or 2 equations that we need to go through it. I think if you look at this kind of a, let me draw this beam with you. So this is 300 by 600 millimeters, the 3D. I hope you can imagine this with me as well. Let me draw it up a bit more. I hope it makes sense. And this length from here to here is 5000 millimeters. What they want is basically we have support here at this corner and support here at this corner. Now what they want that, okay, what would be the load that is uniformly distributed load as a line load? That's apply the line load. As you can see, that's line loads need to be calculated N, right? and that's the unit for this line load, let's say kilonewton per meter. And later they want to know what would be the point load P. Now for this case, basically this is concrete beams. So if you want to calculate the UDL load, uniformly distributed load, in kilonewton per meter, I would have density of the concrete, because it's a concrete material, let's say kilonewton per meter cube, times by the perpendicular area where I want to calculate the UDL load. Now for density of the concretes, we're going to use the Australian standards. As I mentioned, please keep this standard handy for your use. We're going to use this 1170.1. If you open this one and go back to the appendix A, unit weight of the materials, I would encourage you to scan through it in your own time, read all the materials. They are construction materials, easy to read, nothing super complicated. But particularly for these examples, we are going to use concrete, and for unreinforced concrete you have 24 kilonewton per meter cube. If you are adding the reinforcement 1% of volumes, they have not given anything, then you just need to add 0.6 into this one. So for our case, let's take it 24.6 kilonewton per meter cube. Let's assume 1% reinforcement. That's what it's given. Times by perpendicular area. So look at this red one that we want to use it. So if I want to calculate this red one, the perpendicular area that I like to take into account is this one, right? This is parallel area, by the way. This round one that I'm putting is a parallel area. So when I want to calculate this red one, then I would just multiply by 600 by 300. So 0.6 meters by 0.3 meters. I just convert this one into meters. So let's use the calculators. 24.6 times 0.6 times 0.3. It gives me 4.43. Let's take it 2 decimal places. 4.43 kilonewton per meter. So that is your first answer, saying that what would be the, let's say this is 5000 millimeter. What would be the UDL load due to the weight of the concrete would be 4.43 kilonewton per meter. Look, you need to always feel it. Feel it meaning that somehow if you screwed up some units here and there for millimeter and meters, just feel it that 4.43 kilonewton per meter. Yeah, it makes sense. That's kind of UDL load is makes sense. If you're getting the million answer, let's say I get 4 million kilonewton per meter somehow in the calculators or some mistake. So go back and check. OK, that's what I always just check the units and check the numbers that is makes sense, not just blindly follow that. And if I want to calculate the point load out of it, I would just put the point load 4.43 kilonewton per meters times by these 5 meters. That will give me 4.43 times by 5 meters, give me 22.15 or 22.15 kilonewton. That is the point load. So that's the first answer. If I want to put in the summary, if I just want to put it in the summary, that if I have any slab, beam or anything like rectangle shape or anything, and someone say that calculate the weight, the line load that are applying, what I would do, let's say someone say that can you please find the line load in these directions. So I would have density for this material somehow from the AS 1170.1, and then I will multiply this by this area, perpendicular area. So UDL load is equal to density in kilonewton per meter cube times by the perpendicular area to calculate. That will give me the UDL load kilonewton per meter. If someone said, can you please calculate the UDL load going in this direction, then you multiply this area. You see, so that's the UDL loads going across in this fashion. So so this is how it's helpful. Another exceptionals that if you are coming across with a wall, let's say brick wall. So in that case, brick wall, something like this is a difference between that brick wall. Brick wall is thickness is smaller. You can look at this. This is 300 millimeters, but this one would be, let's say, 100 millimeters or something. This is thick and these are wide like this. So in that case, if I want to calculate the UDL load that's applied by this wall, is just density kilonewton per meter cube. You can find the density of the brick wall times by this thickness times height. Thickness in meters times by the height of this wall. So that is just an exceptional case for the wall. We will take an examples where I'm going to explain you that in detail. So I think you understand the story. If you have this slab or beam or anything, you want to calculate the UDL load due to the own weight. When you weight it, then it's kilonewton per meter cube. Density, you can find it from the standards times by the perpendicular area to get this kilonewton per meters. And if I want to calculate the point load, then you just multiply by this length. If you have a wall like a brick wall or something, then thickness times this height will to multiply with density. That will give you the UDL loads. UDL load kilonewton per meter is equal to density times by thickness times by height. That is kilonewton per meter cube. This is meter and this is meter. That's just a summary. Now let's jump on to the next questions. Just unmute yourself if you have any questions there. Now, question number 2. Dead load and live load. Calculate the self weight of cavity structure brick walls. As you can see, they want to calculate the brick wall. There are 2 brick walls, by the way. So again, I summarize to you that this wall will going to apply the UDL load in that fashion, right? Combined UDL load. We need to find a combined UDL load. Let's say combined UDL load would be somewhere in the middle like this. So in that case, what we're going to do it, we will going to first find the brick wall. We need to find UDL load in kilonewton per meters. We will say density of brick in kilonewton per meter cube times by again thickness in meter times by height in meter. Right, so let's plug the value. Density of the brick wall. Let's find the density of the brick wall. Ceiling. Okay, by the way, they are in the pressure, ceiling, floor, roof, walls. So I think that will helpful. Walls, and then brick masonry walls, and the burnt clay per 10 millimeter thickness is 0.19, right? So that's will helpful. Table A2, page number 21. Okay, let's put the notes. Table A2, page number 21. We have the 0.19 kilonewton per meter square. By the way, this is given in the pressures. I can show it to you, not a density. So here they have already given you that 10 millimeter thickness, 0.19, as you can see here, and the unit is kilonewton per meter square, right? So for that case, this is per thickness, okay? That is thickness 10 millimeters. Now, if I want to calculate, let's say 0.19 kilonewton per meter square for 10 millimeter thickness, I want 100 millimeter thickness, right? It's given in the figure 110. So we want 110 millimeter thickness. how much the pressures that going to be applied. So 0.19 times 110 millimeters over 10 millimeters. So use your calculators. So it is 2.09 kilonewtons per meter square. Right. So now you have already take into account thickness, because we no need to worry about thickness now, because your thickness per thickness we already done. And this one is pressure. So that is given in the pressure, kilonewton per meter square. So that would be 2.09 kilonewton per meter square times by the height. Height is 3 meters given here. So would gives me 6.27 kilonewton per meters. Now the one wall applies 6.27, but we have two walls. So for two walls, we will have 6.27 kilonewton per meters times by 2. You get 12.5 kilonewton per meters for two walls. So if I want to just draw this wall, let's say supported at some stage, some supports here, some supports here, then this wall is these two walls carrying the UDL load of 12.5 kilonewton per meters. So I hope it is makes sense that from standards, from these standards, we find the brick masonry solid wall 0.19. You can assume one of these calcium silicate, or if you don't, okay, the decision should be like this. If you don't know which one to take, burnt clay or calcium silicate, I would go for higher because it would be conservative. It will work here. Okay, but if it is specified, you clearly take it 0.19. But that is for 10 millimeter thickness of the wall. That's 0.19, and the unit is kilonewton. So first of all, I convert this one for 110 millimeter thickness. So that was conversion that I made, because it's easy. If you know this one by 10 millimeters, then what would be the 110 millimeter? Just math that you can use. Now, once you know how much pressures that is applying from the 110 millimeters, then you can just multiply by the height of the wall to convert into kilonewton. Pressure conversion into kilonewton. So the summary again. Let me summarize the things again. So if you have a density given to you, and then you want to calculate the UDL load, you multiply by area. But sometimes it's given in the table A2, all given in pressures with the thickness. So if someone give you pressures, let's say someone say that, let's say this is kind of a pressures, right? Let's say someone give you pressures like this is a pressures per area. Let's say kilonewton per meter square. So before we take a kilonewton per meter cube, then you multiply by area to get the UDL load. But if there is a pressures given to you and you want to convert pressure into kilonewton per meters, you say that pressures, that you can read it from this one, kilonewton per meter square times by the perpendicular length. Perpendicular length meaning that if you want to calculate the UDL load due to these pressures, you multiply this length, perpendicular length. Now, if you want to calculate in that fashions, then you multiply this perpendicular length. One exceptional though, that if you have wall standing like this, and that will causing the pressure here, that you know from this, this is the tiny pressures, then you just have a UDL load for wall is pressures kilonewton per meter square times by the height. That is meters, and that is your height. So I hope it's making sense that you might come across with two, because table A1 give you kilonewton per meter cube. Table A2 on the other hand give you the kilonewton per meter square in terms of thickness. All thickness are just divided. So what happens here, kilonewton per meter square, they take a thickness of this one and they divide by thickness to make it, they multiply by thickness to get it kilonewton per meter square. So that's just the thickness, they take it out from here and they make it kilonewton per meter square. So if you come across kilonewton per meter square, don't worry. If you have this sense, if you have this sense, you can just multiply by perpendicular length. If you have wall for pressures, you just multiply by height, because basically you want to read off 1 meter from here, right? Because you want to have kilonewton per meter. So somehow you want to get it out these meters. In here, you have kilonewton per meter square, but you want UDL load kilonewton per meter. So you try to take it off 2 meters square. So you just multiply by area. But which area you just imagine that, okay, this is the things. I think I have one kind of there you go. This might work a bit more if I can. Okay, so if I have this kind of a block or this what can I say? There's a formwork. So if I have this one and if I sitting it down, and this will apply the line load. You can see this will apply the line load. So density of this times by this this area. That's you are calculating. If I want to calculate the UDL load in that fashion. Let's say this another examples probably. Let's take more examples. Probably that will give you more idea as we make more practice. Now here, calculate the uniformly distributed dead load WG. And by the way, let me add one thing. The standards, the dead load standard will, and that is denoted by capital G. Standard said permanent action. Permanent action, that's the vocabulary they use, and they denoted by G. Live load, we denoted by Q, also standards, and they call it imposed actions, the standard. Same thing, and they also denoted by Q. So when you see G, look at this G that is appearing here, that G and W is load, supported by, so G is the dead load, supported by floor beam A, which is to be self weight of 0.4 kilonewton per meter. So what they want is, I think I have it out, so I need to explain it clearly here. What they want is that, okay, you have this tiny beam sitting here. Let me close this standard so it will not distract anything. So here you have this tiny this beam in the middle, A beam. It is going this way, and this beam is carrying this slab. Look at this slab. All right, so it is holding these slabs, and also it is holding this terrazzo paving. Paving is like a decorating materials like tiles and all. You know, when you have slabs at your homes or residential apartments, sometimes they use tiles on the ground level. So, so these are the carrying some kind of a thick 16 millimeters terrazzo paving. So these beams that they need to carry their own weight, right? And by the way, they will apply the UDL load on this line load, kilonewton per meter on this beam. So this beam need to carry its own weight. Then it need to carry this slab that is going to come on it, and then it need to carry this terrazzo paving. So it need to carry 3 different loads. Number 1, his own weight. Number 2 is slab. Number 3, it's need to carry this terrazzo paving. So let's work it out one by one, and we will consistent with the unit that this will be in the kilonewton per meter. So let draw up here. All right, so these guys going to apply the load in that facets, right? So that's we're going to find. So it's going to carry three different load. Number one, self weight of beam A. What is the self weight of the beam A? 0.4 kilonewton per meters, given in the question. So 0.4 kilonewton per meters. This is number one. Number two, it will carry this concrete slab. So weight in kilonewton per meter for concrete slab. Now, we done the concrete slab before. You remember that there is a theory that we just need to play here, that UDL load kilonewton per meter is equal to density kilonewton per meter cube of concrete times pi by the perpendicular area. What was the density for concretes? You remember? In the question number 1, we done it, right? Density of concrete. Anyone remember? Concrete is the most usable material in the world. Man-made materials. You can see concrete around. If you are sitting at your home, you will see the concrete. You will not find the place where you will not going to find a concrete where you have man-made structures. So we must know a few of them by heart. So we don't need to remember, but by practice. So what do you think? This is here, table A1. Concrete, reinforced concrete. Slab generally make with reinforcement. It's not always, there is no plain, we need to put a reinforcement in a concrete. So 24 plus 0.6, 24.6. That we can make it 24.6 kilonewton per meter cube. Now perpendicular area. There is a theory that I need to explain. I think Heather just briefly touched on that one. So let's demonstrate that. Look, this beam, this part, the half part of this slab will goes to this beam, and the half part of the slab will goes onto this beam. Do you agree? Because these two guys are carrying this whole slab. So out of 36, so 3600 divided by 2, you get 1800 taken by this one and 1800 taken by this one. Do you agree with me? And if I come this side, and these beams will going to share the weight from this beam to this beam. So it will get 1500 here. So this guy will have 1800 plus 1500. It gets 3300, 3.3 meters. It will going to be carried by these beams. I can explain you this one. Just keep in mind on these figures. Let me draw it up the pictures. Okay, now here is your beam A. Here is your slab, 125 millimeter thick. Here is this paving, 16 millimeters, I think, thick. This is slab. This is paving. There is one more beam sitting here, and there is one more beam sitting here, right? I hope you can imagine. From these guys to here is 3600 millimeters. From here to here is 300 millimeters. Now for this one, I would say that this guy's going to carry the slab only 1800 millimeters, and this guy is going to carry 1500 millimeters. Right? I hope you understand that. That is half of here, half of here. So this will carry this slab by 125 by 3300 millimeters, right? So this guy, the area, the perpendicular area, because this guy is going to carry the density times by the perpendicular area. If I have UDL load going on this direction, the perpendicular area would be this 3.3 meters times by this thickness, right? So I hope you can imagine that. So these guys will have this density area 3.3 meters that we just calculated times by this thickness 0.125 meters. So the slab will going to apply 10.15 kilonewton per meter load. That is the second one. The third component that we got is paving, 16 millimeter paving. Third one, we need to calculate in kilonewton per meter paving, and that is 16 millimeter thick. Okay, let's go back to the standard and find something. Okay, so here, if you come back here, this is the floor materials. So ceiling, floors. So come back here, floor. Terrazzo paving, 16 millimeters. You have 0.43 kilonewton per meter square, and it's lucky 16 millimeters. Otherwise, we need to convert it. But I think it's already given in 16 millimeters. So 0.43, we take it as a pressure. So UDL load, kilonewton per meter. Now we have pressure, kilonewton per meter square. Then if you have pressure, we need to multiply perpendicular length in meter. So the pressure is 0.43 16 millimeter thickness. So 0.43 kilonewton per meter square, and the perpendicular length. This paving is going to apply the UDL load along this direction. So the perpendicular length become this one. And for that terracotta paving, again, this 3300 millimeters, that's the length that it's going to carry by this beam. So 3.3 meters. So 0.43 times 3.3 meters, you get 1.42 kilonewton per meter. That is number 3. So let's add them all, because the UDL load kilonewton per meter on beam A is a self weight of the beam, slab, and paving. So self weight is 0.4. Please make sure all the units are same. If you sum them up, 0.4 kilonewton per meter. Number 2, slab, 10.15 kilonewton per meter. Number 3, 1.42 kilonewton per meter. So the final answer, 0.4 plus 10.15 plus 1.42, you get 11.97 kilonewton per meters. That much load that beam A would be carrying. So how much? 11.97. So if I draw it up here, this beam A would carrying 11.17 kilonewton per meters due to the own weight of that beam A, due to the weight of the slab, and due to the weight of the paving. The additional concept that we added in these examples is to calculate this sharing perpendicular length. So let's revise that what we covered so far. If you come across with density and you want to convert to the UDL load, you multiply by perpendicular area. How come you're going to come across with density? Because this table A1 has noted this kilonewton per meter square. That's it. Anyone, if you have density, convert into UDL load, multiply by meter square, there are a couple of meters square, just check the perpendicular. If you are considering UDL load in this fashion, so this is the one and this is a perpendicular. So you can imagine perpendicular. This is parallel. So if you can't imagine, you can draw the line instead of this one, and then you draw a perpendicular line like this, and then you draw perpendicular. That's how you can calculate area, right? And this one is parallel, so this is perpendicular area. So this line and this line. If you have this line, then this area. Now this is the first concept that we covered. Now you might come across in table A2, where they just get this meter square, a meter cube read off by taking the thickness. So they have give you all this weight in terms of thickness, but they will make you pressures, force per unit area. So if you have pressures, if you come across pressures like any units that you have it in pressure, and of course they have thickness, so then pressures times perpendicular length, like we done it in our examples for this, like this one. This paving will cause the pressures, right? And then if I want to calculate UDL load for pressures, you just multiply by the perpendicular length, right? So the UDL loads goes this way, the perpendicular lengths across this way. So that's pressures. For the pressures, keep in mind, if you come across walls, you just need to multiply height instead of perpendicular length. So that is just the exceptional case. Just keep in mind this one. So that's two things done. That's we covered. Now the last bit that we covered is this. So if you come across with this kind of sharing load between the beams, you might need to calculate the floor. I think they use the vocabulary tomorrow in the workshop. I will tell you that vocabulary, that you just need to calculate the half goes here and half goes here. So you can't just take it this. If you take it 3.6 plus 3 and put 6.6 here, that would be wrong. So if you come back here and you put 6.6 here, it will underestimate your significantly. You can see 6.6, right? So that is not the case, right? So it is just 3.3 meters. So it's not 6.6. Okay, so that's we covered so far. Any questions, by the way? Nope. Okay, now we will like to calculate the average uniform weight of the roof in kilopascals. So far we are calculating in kilonewton per meter. Now they want you to calculate the weight in pressures. You can see that questions can be changed. Last three examples we are calculating in kilonewtons. They want it in kilopascals. Now is a flat roof and at 10-degree pitch. So I think the roof, I will just show it to you if I have. I think you have seen these kind of like a standard roof, right? You have these purlins. You can see these purlins are these members like this. This is a ridge. Parallel to ridge is a purlin, and then you have these other batons as well, and then you have a roof seat, like a roof seats, right? So that's just an imaginations for you to which help you to imagine this one. So you have corrugated sheet 0.5, like a metal sheets on the roof, that is on this. You have purlin cross section, they are timber purlin, hardwood purlin, center to center distance 900. What does it mean? That if I have purlin here, if there is another purlin here, another purlin here, so center to center distance between these two purlin, from purlin here, because there might be another purlin, another purlin, another purlin, so that center to center distance between the purlin is 900 millimeters. Then you have softwood batons. Again, if you go back to the batons and then batons like this, you have these cross sections and give you the center to center. By the way, if you're looking from this side, you will have these cross sections appearing. And you have plasterboard ceilings. Now when you are inside the home, you are sitting at here. If you are watching up on your ceiling right now, then you will see the ceilings first, plasterboard ceilings. Inside the plasterboards, you will get these horizontal batons and then purlins, and then you will have this roof. So now we need to calculate the weight for all of them in kilopascal. That's we need to calculate. Let's do it one by one. Let's work it out from top to bottom. So let's say start with CGI and the corrugated sheets. And by the way, we need kilopascals. Keep in mind kilopascals. We need kilonewton per meter square. So let's start with CGI. CGI. Go to this roof one here. If I have it ceilings, the floor, roof. Roof sounds interesting. Yes, roof, fiber, acrylic, steel, steel seatings, flat, galvanized per meter cube. Yes, steel, galvanized, corrugated, right? Corrugated seating. So that's CGI. That sounds promising. Table A2, page 21. And what's the thickness? 0.5, I believe. Thickness is 0.5. So for that thickness 0.5, we will get 0.5 including lap and fastening, 0.05 kilonewton per meter square. 0.05 kilonewton per meter square, and that is kilopascals. 1 ton seconds. We will come back to the second one. Is after the seatings we have purlin, hardwood purlin. Hardwood purlin, we need it in the kilonewton per meter square. Let's do it. Hardwoods, I think this is the timbers. 12% moistures, 1720. We will teach you this. Australia and New Zealand. So I think gray iron bark is the hardwood. That's the weight of hardwood, 11 kilonewton per meter cube. So gray iron bark is the Australian timber type. So is a gray iron bark. Hardwood is a kilonewton per meter cube. So the density for purlin hardwood is 11 kilonewton per meter cube. Now we need to convert this kilonewton per meter cube into kilopascals, right? You remember cross section area, this concept, the first one that we introduced. If you come across with density, let's convert into UDL load in the first, right? So let's say perpendicular area, and the area for this one would be 150 by 50. So 11, 150 meaning 0.15, and 50 meaning 0.05 meter. You get 0.0825 kilonewton per meters. But we don't need in UDL, right? We don't need this UDL. We need in the Pascal. So we just divide it by center to center distance meters, divide by 0.9, you get 0.091 kilopascals. Someone might say, how come you multiply by 0.9? Where this 0.9 come from? That 0.9 come from the center to center distance. And someone might say, how come you divide that one? So first of all, this is a purlin. Look at this purlin, right? There is another purlin here. Okay, another purlin here, 900. Now this purlin has a density 11 kilonewton per meter cube, right? And it has a cross section area 50 by 150. So this will create the UDL load on the roof in that fashion. So we multiply this one, and then if I want to calculate the area, I want to calculate the pressures. So these UDL loads which I'm going to apply it here, then I need to convert it into the area that will going to, I need to convert it into pressures. So I need to take the center to center distance. And by the way, again, there is a purlin going here and purlin going here. So 450 on, sorry, half 450 here, half 450 here. So that's how it's making 90. So these will become a tributary area for this one. So first of all, you remember that if you know the pressures, then you multiply by the perpendicular length to the UDL load. Now, if you know the UDL load, then you can just divide by perpendicular length, right? 900. So it's just working opposite. Working opposite meaning that that if you know the pressures, then you can calculate UDL load. But if you know the UDL load, you can calculate pressures. You understand what I'm trying to say? That you can go back from UDL load to pressure, just dividing by perpendicular length, then you will have pressures back. Or if you know the pressures, you can convert UDL load. But questions wants pressure, so we first find UDL load first, and then you divide by this length. I hope it makes sense. So this second one done. Softwood, same story. Number 3, softwood. The density of the softwood would be here, Douglas fir. This Douglas fir is 5.5 kilonewton per meter. That is softwood. So density 5.5 kilonewton per meter square times by the perpendicular area. This 38 by 50. So 0.038 times by 0.05 meters. So you will get 5.5 times 0.038 times 0.05. You get 0.01045 kilonewton per meters. But now we need the UDL. We need the UDL, sorry, kilopascal. So just divided by center to center distance. I already explained you that 450. So 250 on each side, therefore it becomes 450. Divided by 0.45, you get 0.023 kilopascals. Number 4, I think ceiling. Now the ceiling, we can go back to the standards. Ceiling here, gypsum plasters or something. What was the vocabulary they use? Gypsum plasterboard ceiling, 13 millimeter. Okay. Gypsum plasterboard ceiling, 13 millimeter. We can take it 0.13 straight away, kilopascals. And it's already given in the kilopascals. So all good. 13 kilopascal. Now we will all add them up. So first one is your 0.05 kilopascals, which is your seating. Then hardwood 0.091 plus softwood 0.023 and plus this ceiling plasterboard kilopascal. So if I just sum them up, you get 0.294 kilopascals. So that is the answer for first one. Flat roof. Now if I make this roof just at an angle at 10 degrees Celsius, I hope you understand this. You have this, everything this one just lift up this lift up by 10 degrees Celsius. So so if I already know that I want to fly, this is flat one, we already calculated how much. The flat one we already calculated 0.294 kilopascals. Now I want to calculate this at an angle. So if I have cos 10 degree equal to adjacent over, let's put this one pitch one, 10 degree pitch. So I want to calculate at 10 degree pitch. So pitch equal to 0.294 over cos 10 degree. You get 0.297 kilopascals. So that is for second answers. I hope it is makes sense. Unmute yourself if it is not making sense. I think we cover the one more concept here, converting from UDL to pressures. But I think it's clear. I think let me know if any details that things that is not clear, which value coming from where, or we don't follow any standards. The recipes are same as I discussed. Now all the way so far we calculated the dead load, like the weight. What about the live load that we're going to get it? Then non-trafficable roof. Non-trafficable roof meaning that's for industrial set. Non-trafficable roof meaning that that's, for examples, in our roof residential apartments and our residential buildings, we will have non-trafficables. We don't have car going. There is no car park. Like car park is the rooftop car park is a trafficable roof, but this one is non-trafficable. Non-trafficable means we just go for maintenance or something. Determining the imposed load Q for which typical purlin should be designed. I already mentioned this purlin, that we need to find where is the drawing? Oh, here. This purlin, this guy's purlin here, that we need to how much load, the live load coming on to this purlin. If I want to design that purlin span is 500 millimeters and are 1200 millimeters center to center distance. So 5000 millimeters span and center to center distance. So 5000 millimeters span meaning 5000 millimeters along this way, and center to center distance is 1200. This is the purlin, sorry. So 5000 millimeters, 5 meters this way, and then center to center distance between the purlin is 1200 millimeters. Now for this case, I think we need to go to the live load of the standards. Now if you come back here on some page here. Okay, here you go. Table 3.2. Oh, sorry, you're not seeing. Table 3.2. Reference value for roof actions, live load, roof and supported elements, live load, street awning including claddings. We not worry about that. Other roofs, that would be the better one. And for that uniformly distributed actions, kilopascals, we need to use this 1.8 over A plus 0.5, but not less than 0.25. So that's the notes. So if I want to calculate the live load for roof, live load for non-trafficable roof, then in kilopascals equal to 1.8A plus 0.12, right? And the unit is in kilopascals, but should not be should be greater than 0.25 kilopascals. We can't make it less than that. Now A, what is the definition of A? A is a planned projection of surface area of the roof supported by the member under the analysis. Now what is planned projection area? I need to explain that. Now the planned projection area that you're going to get is like if you let's say you have this kind of roof, right? Just let's say you have this kind of a roof. Now let's say plan projection area, meaning that let's say take this half triangle. So if I take a shadow, then this will be the projection area, like a shadow. So if I have this, well, if I have this one, then the plan projection. So if I look at this one, so this is the plan projection, the bottom surface of that one, that is the plan projection area A. So if I want to calculate this plan projection, so I need to calculate this distance and this distance. Now for that one, we already know this is 5 meters because it's a span 5 meters. So we need to calculate, because this is at an angle at 15 degrees Celsius. So this is 15 degrees Celsius. So we need to calculate this horizontal distance, and this center to center distance is 1200 millimeters given here. So we need to calculate this. So cos 15 is equal to x on 1200. So x is equal to 1200 times cos 15. This gives me 1159 millimeters. Right, so we found this 1159 millimeters and 5 meters. So the area would be 1.159 meters times by 5 meters. That is a plan projection area, which gives me 5.8 meters square. Now this is the hardest part, to calculate the area. Now if you want to calculate kilopascals, you will get 1.8 over 5.8 meters square. I'm just using these equations, plus 0.12. So let's use this. We get 0.43 kilopascals, which is greater than 0.25 kilopascals. Therefore it is okay. So if I draw the purlin, which is 5000 millimeter long, you will have the live load is 0.43. This live loads coming from the persons walking onto the roof, the maintenance persons. So I think